Hi y'all. So today I'm going to work through the exam 3, and unfortunately I don't have a blank copy of this. I only have the one where I always work through the exam to make sure that the answer key that we're not missing anything. So I'm just going to cover up my work as best as I can and then just work it for you on these blank sheets of paper. So the answer key is already posted, so it's not like it's a surprise what's going to happen, but I'll tell you sort of how my thought process was for each of these questions and how I ended up choosing the answer I did. So, whenever I see an acyl chloride of any kind, I'm assuming that it's going to, this isn't a benzene ring, that it's going to be the leaving group and it's going to be replaced with a nucleophile. And usually these are weak nucleophiles. So initially it'll be nucleophile with an H plus, and then that will get deprotonated. So I kind of have this idea. It's like if I have a chlorine, an acyl chloride, and then I have ROH in H2H, HOH, any of these with the acyl chloride will end up substituting the leaving group for this. So you'll end up with OR in H2 or a carboxylic acid, right? So that's kind of what I think when I see this. So without even working the problem, and this doesn't take into account any other reagents you need. This is just kind of like the basic idea that I keep in my brain. So without working this or doing the mechanism, when I see this chlorine and I see, actually I should do this in a different color so it doesn't mix in with my pencil. When I see this chlorine and I see this OR-H group here, I immediately know it's going to substitute out and put this in. So, but I will work through the whole thing for y'all just so you can see it. But I don't, on exams, like if I feel pretty confident that that's what's going to happen, I actually don't necessarily work through it. So the first step is going to be this acting as a nucleophile, attacking. And now that you've seen the next chapter, sometimes people will think like, oh, that's a weak nucleophile, so why wouldn't it do 1,4 addition? Didn't you say 1,4 addition is favored? Yeah, 1,4 addition is favored if you have a unsaturated ketone. So if we had an unsaturated ketone plus this, you might favor 1,4, but that's not what we have. So just be sure to look at what you have before, and we also have a chlorine, which is really good leaving group. So be sure to think about what you have before you make a decision. We have chlorine, that's a good leaving group. We don't have an alpha beta unsaturated ketone, and also chlorine makes this a more electrophilic center, right? Because it's moving, it's electron withdrawing, so it's moving some of that positive or that negative charge away, making this more positive. So all those things together help me know that this is going to attack here and there's not going to be any alpha carbon reactions. So we get this step, and then we're in basic conditions. So I think this would recover first. If it was acidic conditions, it might come and deprotonate down here. Hard to say, honestly, which would happen first. And then we have our O, and that's protonated, and then it'll get deprotonated probably by the chlorine in solution, which would make HCl, and that's why we have pyridine present, so that it can neutralize the HCl, or that it can take the H instead of the chlorine, leaving you with this. So that would be my answer, and that is answer choice A. Okay, the next one, oh, I was so annoyed when I first saw this question. I think it's a good question, but I was like, there's so many things. So I'll tell you what my approach to this was. So the question is, aldehydes are more reactive than ketones towards nucleophilic addition reactions. Explain why. So I realized quickly that the first part of this was about a steric effect in each one. And the second part is about an electronic effect. So one's about nucleophilicity or electrophilicity, and the other one's about steric effects. And so I looked at that and then thought about what I knew to be true. So aldehydes are more reactive than ketones because why? Well, one, if this is a partial positive center, this has one donating group and this has two. So the carbons donate electrons, which make the ketone less electrophilic, less reactive, more stable. So less electrophilic, less reactive, more stable. Basically, they're stabilizing that partial positive, and just this hydrogen doesn't have the ability to do that. Just one carbon group isn't doing that as well as this one. And then the other thing is, if we're thinking about steric effects, then these are bigger groups than this. So the steric effect is going to make the ketone harder to get to, and the electronic effect is going to make this more reactive. So then you can literally see, I looked at aldehyde more sterically hindered. That's not right, because an aldehyde is not more sterically hindered because it has one hydrogen as opposed to having two carbons. So it has one carbon instead of two carbons, so I knew that wasn't right. Again, okay, on this one, I was like, less sterically hindered. That's a good sign. And then it was like, because of the carbonyl carbon, the aldehyde is more electrophilic. Oh, so that seems like a good response to me. But I check all of them just in case. You can literally see I checked every single one. So this one says aldehyde less sterically hindered. I was like, that's right. Carbonyl carbon of the aldehyde is less electrophilic. Well, we know that's not true. The carbonyl carbon of the aldehyde is more electrophilic. So that one's wrong. Not right. These are interesting because I saw this counteracted by, and I was like, the steric effect and the electrophilic effect here are working together. This has less steric hindrance and less electrophilic, so nothing's counteracting each other. So I knew both of those were wrong just by that statement of counteraction. So that's how I approached that question. I don't know if that's helpful to you. That's more of like a test taking tip, is I underlined the words that were different. I saw the pattern and underlined the words that were different, and that made it way easier to work through all these words, because looking at all those words as someone who has ADHD, I was like, heck no, am I reading all those? Okay. Initially, I got this one wrong because I thought it was acidic conditions. You can see that I did that. And then I was like, oh, crap, it's under basic conditions. So I literally do underline keywords. I feel like that's a test-taking tip that we give. And sometimes students are like, yeah. But no, really, it helps me so much to get the right answer if I'm underlining keywords here. So in this case, the question is the nucleophilic addition of aldehydes under basic conditions. So we have a nucleophile and no acid. And this is just like epoxide. So I'm going to kind of do both of these to you, H plus with a weak nucleophile. If I saw this plus this, the first thing that I think is going to happen, O minus, and then the nucleophile. Now, if this was an alcohol, there'd be an H on there, and this would be positively charged. If this is a Grignard reagent, it would not be, and you'd have to add H plus, and then you'd get your OH in your nucleophile, right? So that would be your addition. If it was in acidic conditions, this is probably going to protonate first, and then your nucleophile will attack. Sometimes in acidic conditions, I've seen y'all have the nucleophile attack first, and I'm fine with that for your mechanism stuff, and I usually give points for that. But this is kind of asking, do you know which one of these is more nucleophilic? Which one of these is going to do the acid-base reaction first? An acid-base reaction always happens first, and then other nucleophilic reactions. Acid-base reactions are always the fastest. So that's why we have the proton transfer happen first here. So that's... but this is for acidic conditions, and we're asking about basic conditions. So initially I answered in acidic conditions, but this is actually basic conditions. So nucleophilic attack is first, and then we add the proton. Okay. Next question. I actually initially got this wrong also. It's funny because I feel like it's important to know that everybody gets questions wrong, even people who've been doing this for a really long time. So what's the predicted product form when cyclohexane carbaldehyde reacts with excess 2-propanol in the presence of sulfuric acid? So, this is acid catalyzed condition, so it's going to protonate probably first. And then your alcohol is going to attack. And you'll get OH with this. And then probably this will transfer. And you'll have, so I got to this step and then I was like, does this make sense? OH2 plus and your 2 propanol over here. So I got to this step and I was like, I think I know what's going to happen next, but is this possible? Because the next thing that makes sense to me is this would come down and reattach it and kick that out because it's excess and you've got a good enough leaving group that could happen. And I had to stop. I mean, I hadn't been, reviewing this material because I was focusing on my defense, and I had to stop and make sure that this intermediate would happen. I was like, is this real life? This seems weird. But it does happen. And so I think I just, I was kind of surprised by that. And I hadn't been kind of like honed in on this material. And I forgot that this was even possible. And then this will attack again. And you'll get, and this is what, hopefully you recognize what this is just acetal formation. So this first step, this is a hemiacetal, right? And then with excess, it goes twice, so you get an acetal. But I guess the shape of this isopropyl group was just so weird to me that I didn't recognize it as an acetal formation at first, and I was really confused and had to go look it up, like, will this happen? So I don't know, I just thought that would be interesting to share. If y'all got that one wrong too, you're in good company. You can see, this was my work in pencil. I had this protonate, I had this attack, and then I got to this step, and then my work in pencil stopped, and I went and I was like, wait, am I wrong? And I went and looked it up. And then I had this pen is when a student in class came and asked me to work it out again. So initially I was like, am I crazy? This is what I think is going to happen. And then it ended up that was right. But I did have to stop and go. I got to this point and was like, what? No way. So yeah, I don't know. I just thought that was a kind of a fun story for y'all. Okay. This next question is actually the same exact type of question as the last one. It's another acetal formation question, right? But in this case, it's acetal formation that's cyclic. So we have 6, 5, 4, 3, 2, 1. We have this aldehyde with H+. So again, this will protonate first. Making this oxygen even more willing to come and attack and kick up. And you have to number your carbons on here. So 1, 2, 3, 4, 5, and the oxygen makes 6. So this is a 6-membered ring. So the bond comes from here to here. So this is 6, 5, 4, 3, 2, 1 is where the ketone was. There's a hydrogen that's right here that's implied, so I don't technically have to draw it. And then this is positively charged. And actually, initially, I didn't number my carbons, and I picked 2, and then I was like, I should go back and number my carbons. And then I realized I was wrong. So again, that is why I genuinely number my carbons consistently on when I take exams or when I do these practice problems. Anyway, and then it would probably get deprotonated by the water in solution, and you'd end up with, that's an oxygen right there, this ring. So this is a hemiacetal. So it's very similar to the last question that we saw. But yeah, I think it's beneficial for y'all to see, like, oh, at first I didn't number my carbon. I circled this, and I was like, wait, let me just check real quick. And I numbered it, and I was like, oh, crap, it's actually this one. Okay, what is the most acidic hydrogen in the compound shown? So the most acidic hydrogen is going to be the one that can handle the electrons left behind the most. So if you lose this alpha hydrogen, it has one resonance structure, right? And that stabilizes it. So that's more stable than a regular sp3 hybridized that has a pK of 50. This has a pK of like 20. If you have two together and you lose that hydrogen, it has two resonance options. So it would end up with three resonance structures. So that one's even more stable. It has a pKa of like 10. So the more withdrawing groups around it, the more stabilized the lone pair that's left behind is going to be. This kind of looks like a little spider. It's kind of cute. It's like a bug. Make it a happy spider. Anyway, so this right here has 1, 2, 3 electron withdrawing groups on it. So that's why I picked that. This one has 2 electron withdrawing groups. So I would say it has a pK of like 10. This one has 3, so I bet its pK is like 5, but maybe it's not quite that high. And this only has 1, so it has a pK of like 20, so that's why I picked that one there. This has an electron donating group next to it, so it'd actually be destabilized when the lone pair is left behind. So this, I'm guessing, would be closer to the 45, the regular old ketone, but maybe because there could be a resonance, maybe not. And then this would be, 20 as well, because it's at the alpha. So that's what I think of. I either reason through how many electron withdrawing groups it has, or if I know the pKa off the top of my head. Okay. This next one, actually, I think I can work it on here for you. So PCC is going to turn a primary alcohol into CH2, CH2OH, into an aldehyde. So that's a good review of oxidizing reagents for you. CH2, yeah, okay. And then if you react it with NH, with two R groups, that is an enamine formation. So if you know that it forms an enamine, you can get rid of this and this because neither of those are enamines. So that leaves 1, 2, and 3. And when I look at this, I'm like, ooh, 1, 2, and 3 are all good options off the top of the bat. They have a bond that's 1 away from the nitrogen. All of those are actually enamines. But which one of them are enamines is going to form from what I have drawn here, where I made my my aldehyde. So sometimes to do a shortcut for enamine on multiple choice test, I'll draw the corresponding imine and then draw where it's positively charged, and then draw the hydrogen being taken away from 1 away. And that will be how I arrive at my answer. So I basically just, to draw the corresponding enamine, I basically just swap this out for the N with 2 R groups. But if it has 2 R groups, it's positively charged. So that's kind of a shortcut I take where I don't have to draw the whole mechanism out. This one, I drew like, oh, that's wrong because a nitrogen doesn't have a double bond. But yeah, you can see I did the corresponding enamine with a positive charge and then this taking away. So that's how I ended up getting question 2. The question 1's wrong because it's a that should be a hydrogen because it was an aldehyde. And question 3 is wrong because it had the alcohol. It would have had to have the alcohol here, and then that been the ketone right there. So yeah. Okay. 8, what is the product for the reaction shown? Okay, so when I see this structure, I immediately think protecting group, right? Like the only time we see that is if we have a ketone and we add a diol, right? And it protects it. And this is kind of a weird looking one, but I still see that and I think, oh, that is a protecting group. And for protecting groups, something that I kind of try to remember is if you react this, say, for like with Raney nickel or with a diol, this carbon is going to have 2 oxygens directly bonded to it, forms the cyclic acetal. And so that's where I look for where the ketone is. So this carbon has 2 oxygens directly bonded to it. So this was the ketone. That's how I know. And then the other side would have the 2 alcohols on it. And that's how I arrived at answer choice C. And if you want to practice, it would be worth your time to go through all these and see what they'd give you. This would give you something very similar, but it would have your 6-membered ring have the 2 oxygens, and then that would be bonded to a 5-membered ring. So it's very close, but the point that has the 2 oxygens directly bonded to it is on the 5-membered ring, and here it would be on the 6-membered ring. This one would actually look like so you can see as I'm drawing it out, I drew my aldehyde and I drew where the 4 points bonded to 2 oxygens is. And then I know that the is bonded to a 5-membered ring. So it would actually look like this. So totally different because it's not, the ketone's not on the ring itself. And same with this one. It would look like this, only the 5-membered ring would be the one down here. And this would be the 6-membered ring. And then this one down here would be a 6-membered ring with a 5-membered ring on it. Oops, like that. And then the ketone, it would look something like this with a 5-membered ring on that. So it has like one more ring than you need. It has 4 rings instead of 3. So anyway, that's how I came to my conclusion that answer choice C was the right one, is I just basically looked to see where my ketone started. So that's kind of how I reverse do protecting groups, as I don't work my whole way through it. I'm just like, oh, I recognize this as a protecting group, and I know that the place that has 2 oxygens is bonded to it is the acetal that used to be a ketone. Okay. Oh, this is kind of I don't want to say an easy one, but if you can just remember that imines and enamines, when you add them to H3O plus, they reverse, and that'll help you with the storic enamine synthesis of 1,4-Michael addition. But it'll also help you if you just know that, then you can get answer choice D because there's no other ketone there. So if you added this ketone plus this amine, the enamine you would get is this oxygen just basically gets replaced by this nitrogen. It has this positive charge and that gets deprotonated, right? So you end up with this. And then to reverse it, you just add acid and heat and it goes back to the things that it started with, plus NH2. So this is kind of what I am like, oh, if I reverse it, it'll just go back to this, but it's in acidic conditions. So while it's in acidic conditions, this would be NH3 plus. So that's why it's Na3 plus and not just NH2. But if you just only know that you're just turning this back into an oxygen, you could have got that question right. So try to keep that reverse reaction handy in your brain. Okay, this is a good leaving group plus H in H2. So when I see a good leaving group, this is a good leaving group plus H in H2. I know what that's going to make. So that's the first thing I wrote down when I saw this, is I thought of that. So if you just only know that, you can narrow it down to C, or if you're not sure about the bond on the other side, E. But if you just know that this is going to be the major overall reaction, you can narrow it down to be, you can get rid of this, this, and this, and you can end up with these. Now, this one, if you had acid and water after, you would get this, but that's not what we start with. Okay, so that's my initial thing, but I did go ahead and work out the mechanism. As you can see, have this amine attacking here, and we get O minus. This oxygen is still bonded. And then we also have NH2 plus. So this is going to deprotonate, and you'll get OH, O plus NH with this ethyl. And this could get protonated again or not. It doesn't super matter. I think it would probably get protonated from I don't know, actually. I'm going to have it recover and kick this out first before I worry about proton transfers, because I'm assuming that this will happen. So before I worry about proton transfers, whenever I'm not sure where the proton's coming from, I'm like, I think this will be what happens next. And I have this O minus. Plus this has a hydrogen on it. Okay. So I get myself to here, and I'm like, oh yeah, and then now this oxygen can just take this. So if you're ever not sure about the proton transfer, honestly, I feel like it was a real game changer for me when I realized if I don't know about what proton is going to transfer, I can just say, like, I think this is going to happen, and I'm not going to worry about where it comes from, but I'm going to think about the big picture, which is what I did here, and I'm going to come up with my answer based on that. So it would have been easy for me to get caught up and be like, is another proton going to transfer or not? What's the acid base of that? And then I was like, no, stop worrying about that. Instead, just know that this is going to recover and this will kick out, because that's what we did over and over. Over and over, we did. If there's a good leaving group, the nucleophile attacks, this comes up, this comes back down, and that leaves. So I got weirded out by the proton transfer for a moment, and then I was like, stop, focus on the main idea. And that helped me get through this mechanism. So if you're ever not sure, focus on the main idea. And now I drew my amine attacking on the top carbon, just because that's what was easier for me to visualize. But obviously the top and the bottom are the same. This is benzene, so you could just flip it over. So that's how I got to answer choice C. And the big thing that could have tipped you off to this one being wrong is this oxygen just disappeared, and that doesn't usually happen unless you're making an enamine, and this is not an enamine. Okay, or an amine. So what is the predicted product of the reaction shown? So this is just an oxidation reduction question. LAH is a reducing agent. So it'll turn our ketone into an alcohol. So you can see I literally just marked over the ketone and turned it into an alcohol. And I was like, oh, so we've got 3 that do that. So this one's definitely wrong, but these other 3 could be right. So that's kind of where I started. I was like, the ketone went away completely here. That doesn't make sense. All these 3 have alcohol, so I'll eliminate that. And now I'm going to look at the other thing. And then I was like, what happens? This is an amide. It's not just a nitrogen with a ketone next to it. I was like, what happens when amides get reduced? It's definitely not nothing. So that one's not right. And so I could narrow it down between these 2. And then at that point, I just had to remember that amides, when the amides are reduced, they go all the way back to the amine, because you can, I like to think of it as like, oh, you can replace this hydrogen and turn this into an oxygen. And then you can replace this hydrogen and get rid of this completely, because you have a more or you have another heteroatom that you can pay attention to. But that's just kind of how I remember it. That I think you might just have to memorize and recognize in context. But that's kind of how I think of it. Okay, which of these is a keto-enol pair? So whenever these questions come up, I draw a keto-enol pair, which maybe that's stupid, but it helps me see it. And then I just look for that. So this one, this is not an enol. That would have to be an enol, so that's wrong. This one, again, this would have to be an enol, so that's wrong. This would have to be an enol, so that's wrong. So the only answer choice is A. That's the only one that has the double bond directly adjacent to the oxygen. So that's what I'm looking for. Like, it has to have a double bond right adjacent to the oxygen for it to be a keto-enol pair. What are the resonance structures of the enolate formed when the given ester is treated with a base? So you can actually see I drew in the enolate. If it's easy, like if it makes sense to you and you want to do this, you're more than welcome to. You can draw the base, draw the hydrogen taking it and coming and kicking up. And this is one of your enolate resonance structures right here. There's an oxygen there. And that's this one right there. And then this is going to come back down and kick out, and then you'll get the lone pair there. Oxygen. And it has a methyl group, so that's this one right here. And then none of these other resonance structures make sense. When have you ever seen, if you just think, when have I ever seen a ketone with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons? Like, this is violating the electron pair. If you just can recognize that's a bad Lewis structure, you can narrow it down to only 4 answer choices. Same thing here. If you can just recognize this is a bad Lewis structure, what's the formal charge of this? What's the formal charge of an oxygen with 3 things in one lone pair? It's positive. That's a hydronium ion. Why is this negative? This should be positive. This is a bad Lewis structure. So you could eliminate those two based only on that. And then you have to figure out about this one. Weirdly, there's again only one lone pair here, so that doesn't super make sense. There'd have to be another implied lone pair and then another one for this to be negative. So like, none of those are valid Lewis structures. So if you just can know those aren't valid Lewis structures, you wouldn't have even had to do that, and you could have gotten A and B. And an Aldol mechanism. Okay, so Aldol mechanism, when I see that, I'm like, okay, this is an Aldol mechanism, and then it comes and attacks its friend. And you get this, and then it protonates. So what attacked was the enolate. So an alkoxide ion would be something that forms the enolate, but it doesn't attack another aldehyde. Hydroxide ion, again, could form the enolate. A carbonyl carbon, that would be this right here. That's positive. That's never, oh man, I was off camera that whole time. That's a real bummer. A carbonyl carbon is a partial positive at the center. That's never going to attack. And a proton's never going to attack. So if you just know that carbonyl carbons are partially positive and protons are positive and they won't attack, you can narrow it down to these 3. But specifically, hydroxide ion and alkoxide ion could only generate the enolate. They won't actually attack at the aldehyde. So that's how I narrowed it down. I love this one. So if you ever see Raney nickel, if you ever see this dithiol plus Raney nickel, it's just going to get rid of this ketone. That's it. That's all that happens. It's just going to get rid of any ketone you had. So if you had this plus Raney nickel, if you had this plus Raney nickel, it doesn't matter. It's always just going to get rid of this. So if you ever see this combo, this dithiol plus Raney nickel, think of me and eliminate that ketone. So, but this one, you don't even have to know that. So if you just know that, then you can answer this question. You get your aldehyde, you get your thioacetal, so basically an acetal with sulfurs instead, and then you get rid of it, and it's just the 3 carbons that are left behind, right? But if you just know what propanol is, you're like, great, propanol, that's 3 carbons. Where did all these carbons come from? They didn't come from this, because that's what's up top. Where did these carbons come from? That's wrong. Again, where did these carbons come from? That's 1, 2, 3, 4, and this looks like it's the hemiacetal, but now you've added it to 4 carbons. That doesn't make sense. This one is right, 1, 2, 3. But if you're only looking for 3 carbons, because prop means 3, then you can immediately narrow it down to 1, 4, and 5. And then you just need to know the Raney nickel trick. Okay. So I'm trying to kind of help give test taking tips so that y'all can apply that as you go through your multiple choice for your ACS. Okay, clearly this one, with all my work on it, I was like, what's happening here? So I'm going to cover this up, and you can really see through this page. Here, this will be easier to see. So butanol, that's 1, 2, 3, 4, plus 2,2-dimethylpentanol, so that's 5. 1, 2, 3, 4. Actually, I'll do this. 1, 2, and it's dimethyl. Okay, so when you first see this, oh, I know what I did here. Yes. Okay, so when I first see this, you might be like, what the flip? Whenever I say what is going to happen, and then I realize I have some ketones and a base, like a OH minus, I'm like, oh, that's a condensation. So then I look for where my alpha carbons are. So there's only one alpha carbon. There's not one here. That's an aldehyde. That's an aldehyde. So there's only one position that the alpha carbon can go. So then I'm like, well, this could react together as a crossed aldol, or this could react with itself. And that's the only thing that could happen. So then I went through and eliminated any that had anything other than that reaction, basically. But I think that takes someone who's seen it for a while first. So I am actually going to do the reaction with you instead. So, and I'm also going to employ a 2 marker situation because I think aldol condensations are kind of hard to see. So this is the enolate that has to form. That's the only alpha carbon that exists. And then we have this over here. So this is going to attack and kick up. And we will get, I'm actually going to draw it this way because I think that's kind of a little bit easier to see. I'm sorry that this keeps going off camera. Hopefully this will help you see more. So I'm going to draw the hydrogen here, and then this is the one that forms the bond. So if we number our carbons, 1, 2, 3, 4, 2 forms the bond with this carbonyl carbon over here. But 2 still has a bond to this ethyl group as well, carbons 3 and 4. So this is the original 1, 2, 3, 4. Okay, so that's our butanol. And then over here, we have a hydrogen bonded to this carbon, O minus, and then this big old chain. Was it 1, 2, 3, 4, 5? 1, 2, 3, 4, 5. Okay, and then 2 has died. Okay, so this is the first aldol addition, which there's no heat, so I think it would stop at the addition product. So I'm looking for something that has an aldehyde and this ethyl group off of it. And then, so you can see I looked for the aldehyde with the ethyl group on one side. And then on the other side, it has this, and I'll go ahead and number this chain. 1, 2, 3, 4, 5, 6, 7. Let's see, 1, 2, 3, 4, 5, 6, 7. So all of the things are lining up. 1 has a ketone, that's an aldehyde. 2 has an ethyl group off of it. 3 has an alcohol. 4 has dimethyl. So 1 I know is good. So then I see this, and I know that the only way this is reacting with, the only way you could get 2 of these is if the 2,2-dimethylpentanol react with itself, but it doesn't have an alpha hydrogen to take right there, so that would not work. So I'm going to eliminate that just based off of that. And then now I'm looking at these other three, and I'm like, nothing is really jumping out at me that I can eliminate, so I'm going to react this with itself. So now instead of having it attack this one, I'm going to have it attack itself. So again, this comes and attacks, and this kicks up, and it's easier for me to visualize it if I draw the hydrogen on this side. So this is carbon 2 that forms the bond right here, and it forms a bond with this O minus. There's still an H there, and then 1, 2, 3, 4. So, and this carbon 2 has an ethyl group off of it still. And then that would add a hydrogen. And so again, I'm looking for the aldehyde with the ethanol group off of it. And 3 has that and 5 doesn't. So 3 is a good candidate. This also has the aldehyde without the ethyl group off of it. So that won't work. So I did work this out completely and look at the 2 ones that could form. But if you were good at recognizing the groups that would form, you technically wouldn't have to do that. But I've been doing this for a long time, and I still needed to work it out. So I think y'all should probably work out a question like that. And then this last one is just which of the compounds shown is the strongest acid. So the strongest acid is going to be the thing that can most easily stabilize the lone pair left behind. So the reason that this is more stable than this is because resonance, right? Now the negative charge is dispersed on 2 different places. So that is how we think of acidity. It's in terms of the lone pair left behind that can be stabilized. In this case, we have the same functional group for all of them, so it's going to be O minus. And there's a partial positive right here, and there's resonance. And so the resonance for all of them is going to be the same. We don't have to worry about that. The only other thing that could be is inductive effect. And what's going to pull electrons away most efficiently are going to be more fluorines closer to it. So right here, if you lose this proton, you have your resonance, and then you also have fluorine pulling the negative electrons towards it. That stabilizes the lone pair left behind even more by spreading it out even more, and that's answer choice E. I don't think I'm going to work these all out for you because your final is multiple choice, not free response. But essentially, this would get protonated, and then this would attack with itself and kick up, and it would form a ring. And that's how that would work. This H3O plus Br2, hopefully you recognize this as an alpha bromination, like we talked about in the last few videos about alpha reactions. And followed by the addition of a base, it tends to give an alpha beta unsaturated ketone. So the trans is more stable than the cis. Actually, technically, cis trans is not correct here because there's 4 substituents. So the E is more stable than the Z. I did see a few students have that product, like the bromine lost that. That's the least stable. But I gave full credit if you said that that was the least stable and that this was the most stable. I'm going to draw this lined up. So the easiest way to see this is if you just have R groups here. You know already that this has a negatively charged resonance structure, and that's partial positive. So this one goes the opposite way. So this is positive, and that can attack. So that's an easy way to remember that this is positive and this is negative, and then that will attack right there. So hopefully that helps you. That's just a quick, easy way to remember that. Okay, this question, Br plus Mg makes a Grignard reagent. Most of you got it right. Then you did a lab where you had a Grignard reagent plus CO2. I'm just going to draw this out for you. And this happens. There's Cl minus. This is just the same nucleophilic attack you've seen over and over, just slightly different. So then after that, you add the acid to get the carboxylic acid, SOCl2, makes this a chlorine, and then excess NH3 will turn SOCl2 into an amine. And then this is an alpha. This is an SN2 reaction basically, but you get an enolate and then you add this alkyl group at the alpha position, and that's, why can't I think of the word? Alpha alkylation alkylation at the alpha carbon. And sometimes people will see this and they'll be like, why don't I get a 1,2 or 1,4 addition? But it's because this is an alpha beta unsaturated. Okay, well, I hope it was helpful for me to work through that with you. And please let me know if you have any questions. Good luck studying.